So good afternoon, everyone, and thank you, Linda, for introducing me. As you mentioned, Linda, I will talk about rouging in pharmaceutical water system, and my name is Per-Ake Olsson. I work for Alfa Laval. I will give a very short introduction. Linda already talked about me. I work for Alfa Laval in Sweden at the moment. I worked also 5 years in Shanghai in China, but now I'm back in Sweden again. Before I joined Alfa Laval, I worked for a pharmaceutical company, AstraZeneca, in Lund, where I worked with the pilot plant in AstraZeneca. But let's go directly to the material that I have prepared and some information about rouging in pharmaceutical water system. Today, I hope I could manage to cover the topics I have here, to talk very briefly about the water storage and distribution loops, because that's where we normally found the Rouge. I will give an introduction to Rouge, talk a little bit about what the regulatory standpoint says about rouging, and then I will go more into explaining how Rouge is formed and how we can avoid or minimize the risk for rouging. If we get rouging, which most of us have, unfortunately, I will then also talk about de-rouging, or how to remove the rouge. And I will also show or talk a little bit about what the guidances say about rouging, different guidances apart from the regulatory guidances. And in that, both the ISPE guidances and ASME BPE guidances come in. But the objective for this session is to give you a brief understanding of the phenomenon of rouging, but also to help you a little bit on how to mitigate the problem with rouging in case you have that in your system. So let's start with the water storage and distribution loop. It's why I'm showing this. Probably all of you know how it looks like. There are many different configurations of a water storage and distribution loop. It could either be an ambient or room temperature loop, or it could be a hot water loop. And as you see here in the bottom, there are many different configurations. And I have actually stolen this as from the ISPE guideline book, where they have given some ideas about how a water storage and distribution loop could look like. And as I mentioned earlier, it's mainly in the storage and distribution loop we see rouge. We can also see it in the water generation, but it's seldom a problem in the water generation, because we have a lot of filtering in water generation, which is removing the rouge particles so they don't come into contact with the WFI or purified water. Why is water system so interesting for rouging? Well, it's due to the specification, the USP water specification. The USP specification is very tight on especially conductivity and total organic carbon, but of course also on bacteria. What is generating rouging is the low conductivity in the water, especially in water for injection and purified water. That makes the water very free from salts and other minerals. So it makes the water very hungry. The hungry water would like to take up other salts or minerals or iron or whatever it might be. And that is what is happened when rouge is generated. But let's go to rouge and talk about what it is, and later on the different classes and how we can avoid it. Rouge is the formation of iron oxide or hydroxide, originating from typically external sources due to destruction of the passive layer. And I will show that how it actually is generated later on. The form of iron oxide, unfortunately, are not soluble in the blood, and therefore they may cause clogging if you inject rouge particles into your blood system. And also in the system, the water system, rouge is not so good, because it will destroy the surface finish on the inner surfaces or the product contact surfaces in your water system. And the surface finish where you have rouge is not at all close to RA 0.4 or 0.6 or whatever it might be. It's very, very poor surface finish. So it means it will also be a very good growing ground for the bacteria and biofilm. However, there are no regulatory authorities that has a written position directly addressing rouging. And but they have other regulatory recommendation on how to avoid particles, secure that you can clean your system, and secure that your product contact surfaces are not contaminating your water or your medicinal product. But we will come as well to that in the next couple of slides. Water or rouge comes typically in 3 different classes. And it's normally the class 1, which you can see on the picture here, has a reddish or orange color. That's the class that is the most common in water system. And it's sometimes called limonite, or it is a ferrite oxide or ferrite hydroxide. This rouge originates from upstream sources and then migrating downstream in your system. And I don't know if you can call a water system for upstream or downstream because it's a circulating loop, but it's generated somewhere in the system and then it gets deposited later on in the flow direction. The second class of rouging is called class 2, and it's also called hematite, and it's a ferrite 2 oxide 3 combination, or ferric oxide. And this rouge is different from the class 1 because this rouge forms in place where you have the problem, where rouge is generated. That's also where you will see the rouge in your system. So it's easier to detect the cause for rouge when you have class 2 because it's just where you see the rouge. That is not possible in class 1. And as you can see in the picture here, you see this is a little bit more grayish or brownish in color. It could be everything from red, blue, purple, gray, and black. What I probably also should say that these class 1 and class 2 rouge is quite easy to remove from the surface, which unfortunately is not the case with class 3 rouge, also called magnetite. And this magnetite is ferrite 3 oxide 4, or it's sometimes called also ferric oxide. This rouge is generated at very, very high temperature, typically in steam system. And it is an extremely stable form, which is good in one thing and bad in another thing. It's good because it will seldom leave the surface, so it will not contaminate your water. It's bad because it's difficult to remove. But the good thing with this is typically it's seldom on the inside of your system. It's more where you have a jacketed tank, which you have a steam heating. And on the outside of the steam heated tank, you can see a black or brownish color. And it means it will not be in contact with the product, but if it is in contact with the product, it will not contaminate. It will not leave from the surface. It will stay there. So we seldom see any problem with the class 3 rouge. It's mainly class 1 and class 2, and that's why we will look a little bit more into these. And I will see now if we could have some poll, Linda and Christina. Do you think that is possible? I have a question. Yes, I can see it now. Thank you very much. I have a question just to find out how common this is in your system. And if you can answer the first question, do you have rouge in your facility? And this is a single choice. It's quite easy. It's either no or yes or I don't know. Just to find some idea how common it is in the system, in your system. And it could be of interest for you as well. And the second question, that is a little bit more difficult question, because many of the company or the pharmaceutical company, they don't really know if it is class 1, 2, or 3 Rouge. But if you know that, it's very good. It helps a little bit to know what type of Rouge you have when you should remove the rouging later on. But hopefully the introduction here to the different classes could give some idea. So this is if you have Rouge in your facility, which class is it? Is it class 1, class 2, class 3, or is it a combination of these rouging, or if you don't know? So please answer that question. And interestingly, we can see that we have 50% that know they have rouging, and only 19% that are sure that they don't have rouging. So we can see it's a quite common problem everywhere. It's not only Singapore. Everywhere I go, I see everyone has problem with rouging. And also when it comes to which type of rouging, I'm quite impressed, because it's more than 50% that know what type of rouge they have or which class. But the dominant is also class 1, which is typical what I always see when I visit other countries and talk about rouging. So very interesting result, and thank you for taking part of this poll. And be aware that there might be some more polls coming up, but the good thing is that these polls are not checking if you are listening or not. It's just trying to find out how the situation looks in Singapore and in your system. Now I will talk about a fantastic book, which is the ISPE Baseline Guide. It's volume 4, Water and Steam System. And in chapter 10, they have it's a special chapter that talks about rouge and stainless steel. And what does it say? Well, first they talk about the regulatory standpoint. And they say that rouge concerns should be focused on whether or not the presence of rouge may be detrimental to the drug products. And they refer to that the FDA has no written position addressing rouging in its existence or presence in high purity water system and process system. But they refer to the Code of Federal Regulation, the subpart D, which talks about equipment. And in the equipment construction, they say that the equipment shall be constructed so that surfaces that contact components in process material or drug products shall not be reactive, additive, or absorptive, so as to alter the safety, identity, strength, quality, purity of the drug product beyond the official or other established requirements. And that means we have to secure, especially with class 1 and class 2 rouge that is leaving the surfaces, can contaminate our product. We have to secure that there are not more contamination that is accepted according to the specification for your medicinal product. But in this section, equipment section, it also talks about equipment cleaning maintenance, and say that equipment and utensils shall be cleaned, maintained, and as appropriate for the nature of the drug, sanitized and or sterilized at appropriate intervals to prevent malfunctions or contamination that would alter the safety, identity, strength, quality, purity of the drug product beyond official statement. So we have to secure that the rouge is not contaminating our water above what is specified in your specification. And also, if we look at the USP, they neither identify rouge as a contaminant, but rather they indirectly defining limits for the components that ultimately will enter the human body. And this is mainly the particles. In the USP, we can see that in part 788 and 789, they have a recommendation of particulate contamination for injections in 788, and in 789 it's for ophthalmic solution. So and typically when you're working with water for injection, you are using this for injectables or for eye liquids. So there is a statement that you must not have more than 25 particles per milliliter that is above 10 micrometer. And where if you have really large particle that is above 25 micrometer, well, they're not really large, but they're larger than 10, then you must not have more than 3 per milliliter. And it's a similar for the ophthalmic solution, not more than 50 per milliliter that is larger than 10, and not more than 5 per milliliter that is larger than 25. So and this is mainly if we look at the injectables, you don't want to inject particles in your blood, because then you could get clogging in your blood system. And also in the eye, it's not so nice to have a lot of particles in your eye when you have any eye solution in your eyes. So this is mainly the only parameter that state rouging should not be in contact. Rouging is not toxic, so it will not kill you by the substance itself. It's just the particles that could clog your bloodstream and cause a problem for the patient. In the ISPE, we can, in this chapter 10, they also talk about rouge formation, and they have quite good information, but they also recommend to the ASME BPE standard to get more in depth into the phenomenon of rouging. And I will go into ASME BPE in the next coming slide. But before that, we take a new poll question to see if your company have any rouge guidance or limitation for water system. If it might be a particulate count in your water, or if it might be any other visible check in your system if you have rouge. So please let us know if your company have rouge guidances or limitations for water system by answering a single choice, either no, yes, or I don't know. And you have some seconds to answer the question. And when all of you have answered, we will see the result. And this is also quite common. I can see that the majority of the company don't have any guidances or statements for rouge, and this is quite common. I think, though, that you should have a particulate contamination, especially if you're working with injectable drugs, and that's also maybe we see 19% have yes. So it's probably when you're working with these are probably working with injectable medicines. So thank you very much for that, and let's go back to the rouge formation. And this is what I think is a good picture, which really explains how rouge is formed. If here you have the stainless steel surface, and on top of this stainless steel surface, you have a passivating layer. This passivating layer is formed by the chrome that you have in the steel. And it's a chrome 2 oxide 3 layer. This will shield off the iron ions or the ferrites from the water, from this hungry water. So these ferrites or especially the water, are very keen to fill up the loose ends in the H2O molecules, because it's hungry. But they can't reach the ferrite ions because there is a passivating layer on top of the steel protecting the ferrite to join the water molecules. But if you have a breakage in the passivating layer, there is, of course, the ferrite ion will merge and join the water molecules, and then you will get these ferrite oxide, ferrite 2 oxide or ferrite 3 oxide. And then you get rouge. These will be particles in the water that will flow along with the water. And when it comes to turbulent areas, it will be smashed onto the surface and get deposited on the surface. It is also that plastic materials, PTFE in the diaphragm, EPDM in the diaphragm or in the gaskets, they will also, like nearly as a magnet, suck in these ferrite oxide onto the surface. So you can also see on the diaphragm valve is typically quite easy. On the PTFE diaphragm, this is a white color, and there is very, very easy to see this reddish rouge. But you know, the PTFE will not generate rouge in itself because it doesn't have any ferrite. So it must come from somewhere else in the system, and it's come from upstream. So this is actually how rouge is formed. And now we have to look at how do we secure we have a strong passive layer in our system. If we look at the passive layer, it's a quite thin passive layer. It's a metal oxide, chromium 2 oxide 3, that is sometimes you can say 100 to 500 ångström, or it's a 10 to 50 nanometer, which is very, very thin layer. It's only 0.01 to 0.05 micrometer. So a very thin layer, and we have to secure that this is a stable layer that will not get scratches or will not disappear. And this is actually how we prevent rouging in our system, to secure we always have a strong and good passivating layer. And the passivating layer you can get with passivation. If you look at ISPE, which I like very good in the guidance, because this is also what we have found in our laboratory. They say, well, passivation helps to build a good thick passive layer on the product. Natural interaction between product and product contact surface, making passivation a short-time effect and showing no general benefit to the corrosion resistance of the base metal. And we have also seen this, that stainless steel is a very good steel to have a natural passivation, as long as you secure that the surfaces are cleaned. Then it will have a natural passivation, meaning that to use a lot of acids, passivating agents to speed up this passivation, it might happen that you get a slightly thicker passivation, but after you have the top of this passivator layer will be degenerated, and it will come back to the same thickness as a natural passivation. So I would say it's not really necessary to do a repassivation, but to do a passivation after welding or polishing could be good, just to remove the contamination that you have on the surface. Because if you have contamination on the surface, you are not able to get the natural passivation, because this contamination will shield off the oxide from the chromium in the steel to generate this chromium oxide. So secure you have a perfectly clean system, then the system will repassivate naturally. So no actual need to do a repassivation. ASME BPE, on the other hand, they say that product contact surfaces of austenitic stainless steel, except those covered by section SD 431, which is process gases, should be passivated before being placed in service. And that's good. It should be passivated before being placed in service to remove the contamination, not really to passivate the surface. But they also mentioned that if you have an electropolished surface, it's not required to do an extra passivation, because the electropolishing procedure is a passivating procedure in the end after the electropolishing. And ASME BPE also have some guidances on how to check if you have a good passivated surfaces. And they say on a good passivated surface, you should have a chromium ferrite ratio that is 1:1 or greater. So you should have more chromium than ferrite on the surface. And it's important that you're measuring this on a depth of 15 ångström. And this is for the passivation. And as you can see, it's the same standard for the electropolishing, which also means that electropolishing gives the same protection as the passivation procedures are doing. And electropolishing have other advantages that makes it even better. And then if we look at the causes of rouge, we can also see here that this is a exposure tests that were made quite for some years ago in the beginning of the 2000s, but it was quite interesting. It was done by Mathisen, and you can find this article. It's coming from Pharmaceutical Engineering, the ISPE book or magazine. They found out that where you have halides or nitrogen or carbon dioxide, you will have an increase for rouging. It's seen both on this XRF, which is X-ray fluorescence measurement that measure the ferrous or iron contamination on, in this case, a Teflon strip. But you can also see it where you look at visually on a Teflon strip if it has rouge. Where you have air, it's very, very weak contamination from ferrite. But when you have air, carbon dioxide, and nitrogen, you have strong contamination. They also checked different materials, and there have been a lot of discussion that you should not use standard stainless steel. Maybe you should try to go to more exotic material and more expensive material like 904L or duplex steel. And it's the same here. They have also looked at the surface finish. When it say plus EP, it means it's an electropoly surface, and the other one is a mechanically poly surface. And you can see in the 316L we have a moderate contamination from iron. And the same actually goes for 904 and duplex steel. Here it's actually strong instead of moderate. But on the Teflon visible, we see rouging on the 904, but very slight rouging in the duplex steel. But again, it shows that the 316L is as good or maybe even better than the more exotic material. And this gives an indication to you that you don't need to go to the more expensive alloy to avoid rouging. It could actually be more difficult to avoid rouging. You can also see here that by electropoly surface, you will get more protection against rouging. And the reason for this is that an electropoly surface makes the surface smoother, and it makes it easier to create this passivating layer after the electropolishing. There have also been a lot of discussion about delta ferrite. Some suppliers say you need to have a low delta ferrite, and that was actually started in 1990 in Switzerland, when there was a Basel norm generated actually by a personal care company. I think it was Unilever that found out, made a test, and they could show that the low delta ferrite content will reduce the rouging in their system. But the tests that were made in this exposure test show that the delta ferrite content have no effect on rouging. What they could see, though, that if you have a product or a surface which is under strong erosion, for example, if we take a tank with a spray ball where the spray pattern is hitting the same spot on the tank wall the whole time, you will slightly erode or remove the passivating layer. And in an impeller, in a pump, you have an impeller. On the tip of the impeller, it could be very, very high velocity. And with this very high velocity, there are risks that small parts from the impeller tip could be eroded away. And when these are eroded away, you get the fresh surface that is not passivated. And then you will get rouging or ferrite particles into your system that is joining the water molecule and create these ferrite oxide rouging particles. So delta ferrite could be a concern to look at if you know you have some product or equipment where you have a lot of erosion. Then it could be an idea to specify a lower delta ferrite content than normal. So to summarize a little bit, what causes rouge? Well, it is the material. and I will come into that. But the sulfur content, when you talk material alloy steel, but the sulfur content is important because the majority of the roughing is generated on the welded areas. Because if you get a poor or bad weld, you can have the surfaces on the welded areas. But the right sulfur content will help you to create a good weld. And then, of course, it's the chromium content that is important, because if you don't have a high chromium content on the surface, it will be difficult to generate the strong passivating layer. And then we could mention the low delta ferrite, but this is only in equipment where you can see that where you need to be concerned about low delta ferrite. If we look on the fabrication, which is also a very, very big problem with roughing. Of course, when you do machining on the surface, you destroy the passivating layer, or when you do welding, you destroy the passivating layer. You have to secure that you repassivate it. But what is probably more important is the actual polishing, or the mechanical polishing. Because when you do mechanical polishing, you are also pressing down the polishing rests, which you can see in this picture to the right here. In between the small scratches that you have on the surface, you are pressing down the polishing residues. And when you have a lot of residues with a lot of surface, because they are small particles, generate a huge surface area, and these cannot be passivated. So you have a huge amount of ferrite with a large surface and which cannot be passivated. So if you don't remove these polishing rests, you will definitely get problem with roughing in the system. And that's why we can see in many tests that electropolishing is preferred, because then you remove all these polishing rests from the system. But we can also see that the process environment has effect. We saw this carbon dioxide or nitrogen or even chlorides or other halides that will increase, but luckily we seldom have these in our water system, so it shouldn't be a problem. But another important part is elevated temperature. Rouge is not developed at temperature below 60 degrees Celsius. But the higher temperature you have in your system, the more you speed up the process of the rouge formation or rouge generation. So it is a recommendation to lower the temperature if possible, and in many cases it is possible, which I will come to in the next coming slide. And here we see the good example of erosion where you have a spray ball in a tank. This is just to wet the surface. So it doesn't really have any reasons to clean, but since it's hitting the same spot every time, you can see it very, very clearly. It's also generate rouge where you hit the surfaces with these static spray ball. If we look at the steel grades, in typical stainless steel or normal stainless steel, there are many different types. We have the European standard, and these are called 14404 or 14435. And then we have the American standard, where you have 316L, and then there is 316L, but it also specifies for pharmaceutical material. It's recommended to follow the supplement 2 in ASTM. And supplement 2 has a specification for the sulfur content. In most of these steel, no matter the European or the American, it has more or less the same chromium, nickel, and molybdenum content, and more or less the same sulfur content. But especially with the supplement 2, you have a minimum amount. You need to have a certain amount of sulfur, and you must not have too much neither. And why is this important? Well, when you do the welding, and if you have a low sulfur content that is below 0.05%, you require a lot of energy to really melt down the steel and to bound the steel parts together. And what is quite typically then, you can miss to do a weld through, so you get the crevice in the bottom or under the weld, but more it generates a very, very wide heat affected zone that makes it difficult to passivate the surface area. Then you might say it's very good to have a high sulfur content, so why not get higher than 0.015 or 17? Well, it is good because you can, this sulfur content makes it easier to melt the steel. So you get a very narrow heat affected zone. But the problem with the sulfur is if it's too much, you will get micron sized pits in the welded area, which then later on will generate pitting corrosion. And these pits or micro-sized pits is a sulfur manganese form, which gives inclusion or porosity in the welded area. So the sulfur content is actually quite important. If it is too low, you will get a wide welded area or heat affected zone. And if it's too high sulfur content, you will get sulfur manganese inclusions in like porosity in the welded area. And both of these will make it very difficult to passivate the welded area. If we look at surface guidances, which surface finish we should have, this is generally not specifically for rouging, but ISPE, they say you can have between 10 micro-inch, which is 0.3 micrometer, up to 0.8 micrometer. And I think that's good. It really doesn't matter, nearly for rouging or for bacteria. But what is good in the ISPE that they say also that the polishing compounds should be confirmed to have been completely removed, because otherwise you can't passivate the surface, and you also will contaminate your water if you have polishing rests on the surface. And they say also that typically around 0.6 micrometer is the most common, and that's good. I would say I see everything from 0.25 to 0.8. And in rare cases, I can see higher than 0.8, and that I don't recommend. But to be anywhere below 0.8 is good enough. ASME BPE, they talk more about the same, I would say, but they also say RA 0.6 is good to aim for. And it doesn't matter if they are mechanically polished or internally electro-polished. But concerning rouging, I think it could be an idea to look for the electro-polishing. We have also done some tests in our laboratory to see how specifically bacteria attach to different surface finishes. But when we tested mechanically polished surface in RS 0.8 and 0.4, but also electropolished surface at 0.4, we saw that the bacteria that were stuck on the surface after cleaning was the same amount. We spiked a surface with a certain amount of bacteria, and then we clean it in the same way. And then we measured the colony forming unit per square centimeter, and we saw there were no differences because the bacteria are quite large. So it doesn't really go into small scratches. So don't overspend on high specification on RA value, because it really doesn't matter in water system. Just to say that for some other system where you are working with smaller particles than bacteria, we could see differences on the particle that were remaining. But what is more important is to look at the difference here between the mechanically polished and electropolished. We are avoiding the polishing residues in the electropolished surface. And you can see that this surface is also much smoother than the mechanically polished surface, and give a lower surface area compared to mechanically polished, which makes it much more easier to passivate an electropolished surface, or to secure that you keep your electropolished or the surface passivated. We made a test also in our laboratory to see the difference between the mechanically polished surface that was not really cleaned in a proper way, and another polished surface that was cleaned in a proper way. We put this in an acid, I think it was phosphoric acid, and we let it stay there for a week. And then we took up the tubes and the surfaces, and you can see how many residues you have in a surface that is not correctly cleaned after polishing. So be careful with the cleaning. Either go with mechanically polished surface that is very, very good clean, or an electropolished surface, because that will also secure that you clean the surface. Temperature was another problem for rouging. The higher temperature you have, if it's above 60, the quicker you will generate the rouge. And I will not read, you don't need to read the whole text here, but it says that you don't need to really be afraid of thermophiles because you have mesophile bacteria in your system. And I will show that in a slide what is meant. But you can read these either in the ISPE baseline guide, that you don't need to monitoring techniques to kill these thermophile bacteria because they are not present in the water system due to the nutritions, the lack of nutritions in the water system. And you can read it also in the guidance book, where it says in high purity water, biofilm growth typically is either minimal or absent above approximately 45 degrees Celsius. So, and this is a sign that we have mesophile bacteria in the water system, meaning that even in a hot water system, maybe you don't need to go much higher than 60 degrees. And I see so many water systems that is operating at 85 or 90 degrees, but it's no reason to use it. What they summarize ISP here is that water distribution system operating above 65 degrees Celsius generally are considered to be self-sanitized. And if you are operating hot water system, you don't need to sanitize, you shouldn't sanitize them. So keep it at around 65 or slightly higher than 65, you are on the safe side for bacteria, and you also have minimize the risk for rouge to develop in the system. When you sanitize, there is a recommendation maybe to go higher to 80 degrees, and this is just a short time you sanitize. And of course it goes faster if you have a high temperature when you would like to sanitize your system. So you don't need to sanitize, and you can have the system up and running soon after that. And they also mentioned that care should be exercised with 65 degrees sanitization instead of 80 degrees sanitization, because we can get heat losses in the system. So secure you have these 65 degrees Celsius in the end of the returning to the tank, because then you are more or less sure that you have 65 minimum everywhere in the system. There is also another comment here about steam, which is very, very good. And they say in this ISP guidance baseline guidebook, steam is typically no more effective in system microbial control than hot water. But it's considerably more complicated because it's generating more wear on the components, and it's increasing the rouging if you have a stainless steel system. And it will also generate safety concerns than hot water. So please don't use steam to sanitize your system, because that will generate a lot of problem for you, and it really doesn't have any effect compared to normal hot water above 65 degrees Celsius. And these are the bacteria classes, as I mentioned. We only see the mesophile bacteria. The curve here is showing the growth rate at different temperature. These mesophile bacteria, they can only survive in temperatures between 10 to 45 degrees Celsius. In rare cases, it can go up to 55 or 50 degrees Celsius. But the thermophile bacteria are not present in water system because we don't have nutrition. It's, as I mentioned earlier, the specification for water, according to ISPE, is very, very low amount of total organic carbon. And carbon is needed for the thermophile bacteria to survive. That's the reason why we don't have them. So in water system, we typically have, we only have the mesophile bacteria, and these are some typical bacteria that we have in a water system. and the upper limit for them where they stop growing or where they actually are killed is 45 and up to 50. So we don't need to speed up too much temperature in our system. In ISP and in other, they talk also about the biofilm. And we know that all the bacteria, or 99% of all the bacteria activity, occurs on the surface in the biofilm. And this biofilm, there is a risk that this biofilm could be an insulator for the high temperature. But if you have a stainless steel system, you're heating up both the surface of the material. Stainless steel is a very good leader of heat. So the heat comes both from below and from the top. So you will still get a quite good sanitization of the biofilm if you're using stainless steel system. But there are also some other guidances which you should look for if you have problem with biofilm. And I have just put them here in the material just in order for you to check later on. I can typically mention that how to control is to minimize the nutrition in the system. Of course, to minimize, because if you have nutrition, the bacteria will grow faster. And that is just to secure you have the hygienic design with the right surface finish and no pocket, dead legs, or crevices in your system. And you should also secure high shear forces, so you remove the biofilm from the surfaces. And also actually avoid hydrophobic non-polar surfaces such as plastic material, because that has a tendency to attract the bacteria to the surfaces, and it will be slightly more difficult to remove them with the high shear forces or velocity. If you have problem with biofilm, you can disinfect them in high with disinfectants in high concentration, or dry the system completely. I talked about this bacteria a little bit when I talk about rouging, because the temperature is so important. And there are a lot of evidence that you don't need to have that high temperature in the system to have a good control of the bacteria. And that will help you for many, many reasons. You will save energy costs, you will minimize the risk for rouging, and you get the system with lower wear. I mean, all the elastomers, they get destroyed the higher temperature you have, and it means that you need to replace them often. So it's only a lot of advantages to reduce the temperature in the system. And with that, I think it's time for a poll question or two questions. And that is to see if your facility have water for reaction. So now we look at water for reaction in the first question. Which temperature is it operated at? So there are single choice question here, either up to 50 or 65 or 75, or is it over 85? When I say over 50, it should mean over 50 but below 65. So somewhere below 50, between 50 and 65, and here between 65 and 70, and 75 and 85, or more than 85. Or you press don't know. And the second question is your facility, if your facility heat sanitize purified water system, what is the sanitization temperature? And here you typically see higher temperature than in a hot water system. So it's either between 75, below 75, or above 75 degrees Celsius, or is it even above 85 degrees Celsius? So please answer these, and I will also answer what I feel is the most common I have seen. And I can also mention that I will share the slides, or ISP will share the slides after, and you also have contact information to me if you would like to discuss more about bacteria, which it could be interesting to control the temperature. And here we can see that the majority is actually saying that it is between 75 and 85, which is quite good in hot water system. it's 27% have more than 85. That's a little bit too high, I would say. Probably we could go between 65 and 75. That could be the optimum temperature. And there are some that also have it there, so that's good. And if you sanitize, we can see that the majority is sanitizing with the temperature above 85, which could be good because then it goes fast. And it really doesn't matter. But there are also some people that goes with steam, and that I recommend to have a look if you can't reduce it to hot water, at least to 90 or 85 degrees Celsius. You don't need to use steam. But very interesting. I see the same situation everywhere. So there are no unique situation with Singapore. I will just quickly go a little bit into the ASME BPE guidance, and I have asked ASME BPE if I can share some of the pages and tables in ASME BPE, and that is okay. They have a non-mandatory appendix in the ASME BPE standard, which is called Appendix D, and it's a non-mandatory, so not mandatory, but I still recommend to follow this appendix because it's the only standard I've seen that is really good explaining the rouging situation in stainless steel. And they look mainly on three things. It's consideration for reducing the rouge formation. It's a little bit the same that I have been talking in the previous slides. And it's also about evaluation methods to measure the rouge, because now they're coming more and more measurement system to measure the rouge, either inline or where you're measuring the water, or it's an invasive method where you actually have to remove, drain the system and measure on the actual surface. So process fluid analysis and surface analysis. And then they also talk about methods to remediate or to remove rouging from your system. And I will show, and you will also, we are sharing these slides so you can see it, read the details here, and I will not do that during the presentation. But what we can see here in the table D21, that is considerations that affect the amount of rouge formation during fabrication of the system. So not during operation, but during fabrication of equipment or system. They see here, they talk about the alloy selection, but they talk very much about 316L type. And they maybe are a little bit too proactive or too positive to super alloy steel or 6 moly type stainless steel like AL6XN. What they mainly also talk about here is the corrosive effects with the higher nickel content. But we haven't really seen that. So I'm not 100% in agreement with ASME BPE here. But they also talk about the mechanical polishing and buffing and the importance to remove polishing residues. And they also mention about electropolishing, that this minimizes both the exposure area, surface area, but also secure you have a clean surface. And they talk about passivation, which is the actual, that's the whole thing with rouging. You have to secure that you have a passivated layer, otherwise you get rouging. And if you have a passivated layer everywhere in the system, you will not get rouging. So of course, passivation is important. They look about the alloy composition, and here it's not only about the nickel content, they talk about the importance of molybdenum and chromium and nickel. And they talk about the welding concerns that I also mentioned about the sulfur content and the heat affected zone. And they also talk about product form and fabrication methods. And here they mainly talk about the difference if it's casted stainless steel or wrought or machined from a bar. And then these are category 3 that have a strong influence on the formation of rouge. And then they also have a category 2, which is moderate influence on the formation of rouge, where they talk about the installation and storage environment, expansion, modification to an established system. And then they also have a table for, as I mentioned, because the previous table here was formation during the fabrication of the system, and the other table is during the operation of the system. And here they talk about corrosive process fluids like bleach and halides. You seldom have that in a water system, but it's probably mainly if you should do chemical cleaning of the water system, which I don't recommend at all. But in some cases, you need to do that. And some cases you still need to repassivate. And then you should be careful that the fluids, chemicals that you add to the system should not etch the surface or destroy the surface finish, because that could generate. But they also talk about high shear and velocity, that then maybe you should look at a low delta ferrite content in order to avoid the erosion. Operating temperature, as I mentioned, the higher temperature, the higher risk you will get for generating rouging. And they also talk about gaseous phase composition, especially carbon dioxide. They talk about application process media, but it's mainly water for injection. We see in buffer media, you seldom have problem with rouging, I would say, because the temperature don't need to be that high. And they also talk about system cleaning. And they are continuing here, looking at redox potential, maintenance of the system, stagnant flow areas, and pressure gradients, and system age. But I leave them here in the slides so you can have a look at it later on. They also have quite interesting information about how to measure rouge, either with a process fluid analysis or with a solid surface analysis. And they talk about pros and cons with different types. You can say in general, the process fluid analysis is non-invasive type, because you're actually measuring the water. So all of these are non-invasive. But the cons is more that can you really measure in the water how much rouge you have on the surface area. And here you always have to work on references. So if you have more rouge in the water, you probably have more rouge on the surface area. But the problem is that you cannot measure really how much you have on the surface area. So these process fluid analysis is more of an indicative way of measuring your rouging. While the solid surface analysis, the problem with them is that they are invasive. But they give you a more accurate information about the rouge that you have in the system. And there is a new system that is tested now that is called electrochemical impedance spectrometry. That is a non-invasive measurement, but it's not 100% or fully tested, so we are not really knowing if it gives an exact information about rouging in the system. They are also, the third part is that they are talking about rouge remediation, or how to remove the rouge. And they talk about phosphoric acid, citric acid, or phosphoric acid blends, typically phosphoric and citric acid, or sodium hydrosulfide, or electrochemical cleaning. And these are for removal of class 1 rouging. There are slightly adding to class 2 removal, where they also add electrochemical cleaning. And for class 3 rouge, they have even more advanced cleaning method. But the problem with the more advanced cleaning method is that they will etch the surface, so it will destroy the surface finish, and that's not good for the long term in rouging. So I would instead summarize this a little bit and do a recommendation that you do this de-rouging typically by recirculating this acid in your system. If you have very strong rouge, you can also put a gel onto in the tank, for example, and you could just let the gel be there for a while, and then you will remove it. And all of these are typically done at temperature between 40 to 80 degrees, and it could take between 2 to 12 hours, depending on the thickness of the rouge layer you have, and also if it's class 1 or class 2 rouge. But the most common, I would say, is for either phosphoric acid to a concentration of 5 to 25. The higher concentration, the faster it goes. But you shouldn't exceed the concentration of 25 or 10% for citric acid, or a blend of phosphoric and citric acid. These are the most common de-rouging media, and it works really fine, and they are not really etching the system. If you go to electrochemical cleaning or oxalic acid is etching the surface, so that is not good for the surface finish. Electrochemical cleaning is a little bit complicated because it's not only the phosphoric acid, you need electrodes in the system, and it could be a little bit complicated to accomplish this. But having this said, I think it's time for the next poll question, and ask, if you de-rouge your water system, which chemical are you using? And here it's a multiple choice question. So is it either phosphoric, citric, or phosphoric blend, or sodium hydrosulfite, or electrochemical cleaning, or are there others, or you don't know? So please let us know. And of course, I understand if you don't know, because you might not work into the de-rouging, but it could be interesting to see. And I will also mention what is the most common way of removing rouge, which probably is the same as you have here with the result. Yes, and it's good to see. It's a combination of phosphoric or citric acid. Citric acid quite high, and it's good because it's also an environmentally friendly acid, more than phosphoric. Or it's a blend of phosphoric and other acid, typically citric acid. And they are lower here on sodium hydrosulfite, and also electrochemical and others. So it's very, very similar to what I see in other countries. And it's also very, very good that we see a majority on these top 3 here, which is the best one. So thank you very much for that. This was actually not the last poll, because I have a poll in the end as well. But I also would like to give some references and further readings for you. I have listed where I have found the information in the previous slide with reference number, and these are referring to the reference number that you see here. And I didn't talk about so much about bacteria and biofilm. There are much more to say there, but you can read these articles here. Most of them, I think, is coming from pharmaceutical engineering. So you can go into the ISPE and search for this article in the pharmaceutical industry engineering, where you see, which are very, very good article explaining why you only have mesophile bacteria and not thermophilic bacteria in your water system. So with that, I think it's time for question and answer. And I've seen that in the chat box, you have raised some question. And I don't know, Linda, if you want me to read directly, or if you would like to read the question.
Yeah, thank you very much for that, Per-Ake. The first question was from Senti Kumar, asking if you could explain more hydrophobic non-polar surfaces.
Yes, and I show that a little bit, but hydrophobic non-polar surfaces are plastic material. It could be PTF. It's any kind of elastomer. Elastomers, they have a tendency to attract bacteria, but also rouge. The easiest way to explain the attraction of bacteria to a plastic surface is if you put the plastic bucket with water, preferably outdoor, and let it stay there for a week. In the same time, you can do the same with a stainless steel bucket. Put that, fill it with water and put it outside. And if you feel on the surface of the plastic bucket, you will get the greasy film, which is the biofilm. But if you feel on the stainless steel surface or steel surface, it will take much more longer time until you get the greasy film on the stainless steel surface or even on a glass surface. And the hydro or the hydrophobic non-polar surfaces, these are all elastomers, and they have a tendency to attract everything to them, not only bacteria but also the Rouge particles. And that's also why you see it on the diaphragm valve, especially PTFE. It becomes red. If you have Rouge in the system, probably that's also very good measuring techniques in the system to check on your PTFE diaphragm. If they are red, you have rouging in the system, and if they're not red, you have very small problem with rouging in the system. So it's maybe the cheapest measuring method, just to visible check of your PTFE diaphragm in the system. So I hope that explains a little bit about the hydrophobic non-polar surfaces and the reason why I mentioned.
Thank you, and thank you for the question. Akil Ahmed asks, please let us know suitable passivation material with percentage and hold time, nitric acid, citric acid, etc. And what are indicators to check the system requires passivation?
That's also a good question, and I would say if you look at the suitable passivation agents, I would say it's the same as the de-rouging, but earlier it was used nitric acid as well, as you have mentioned here. But nitric acid is not so good for the environment. It is really bad for the environment. So more and more, and it's not good for the operator neither. So more and more companies, what I see, would like to prefer citric acid instead of nitric acid. And the concentration and hold time of these, they are, of course, a combination. The higher concentration, the shorter hold time. But it's about the same concentration. It is the same concentration and hold time as was specified in the de-rouging part. So I think you can use these as a guidance. But typically, you maybe order the repassivation or the passivation from an external company, and they should have the right specification. You can read that in an American standard. I have forgotten exactly, but it's an ASTM A200 something, which is explaining how to passivate the system. And there is also, you mentioned what are indicators to check the system requires passivation. Well, I would say if it is a water system, which we talk about here, it's the best indicator is if you have rouging in your system. And the only reason to do something with the passivating layer is if you have rouging in the system. So I think that is the best indicator if you require passivation. But I must say also, if you have a system that is operating, what ISPE are mentioning in the baseline guide is natural passivation gives an equally good passivating layer. But to secure you get a natural passivation, you have to clean the surface completely, remove the biofilm, because if you have a biofilm which is covering the surface, you cannot get the natural passivation under the biofilm. So here it's more of a sanitizing agent that is probably better to do than repassivation, because if you clean the surface completely and have no residues on the surface, you will get the natural passivation, and you can minimize the amount of chemicals that you introduce to the system, which later on has a risk to contaminate your water. And of course, it will also save you money. So my recommendation is actually only do passivation after you have machined your surfaces or weld your surfaces during installation of the system. then it's good to do a passivation. But later on, you don't need to repassivate the system every year or every second year, which I see many companies are doing, but you need to do a cleaning of the system. And you need to do a cleaning anyhow, because when you do a maintenance of your system, you will contaminate the system, and you need to remove these contaminants. Secure that you do this cleaning properly, and also remove any possible left of the biofilm. And then you will have a natural passivated system without adding passivating agent and cost and so on for that. So I hope that answered.
Thank you. Nick asks, what chemical is better for de-rouging and circulation time for de-rouging?
Yeah, I will go back to this recommendation here, because which chemical is better? Well, I would say it doesn't really matter if you go with phosphoric, citric, or phosphoric blends, or combination of phosphoric or citric. It's good. These are safe. You can go to sodium hydrosulfide. It's not so commonly used. And you can also go to electrochemical cleaning, but it's more advanced and costs slightly more. But you shouldn't go to oxalic acid because that is not good for the surface. So try with these phosphoric or citric acid or a combination. And if it doesn't work, maybe you have to go with electrochemical cleaning, because then it should work. But it's a more complicated way of doing the de-rouging. When it comes to circulation time for de-rouging, well, I have written very broadly here, 2 to 12 hours, and it depends on both the concentration and the temperature of the acid and the concentration of the acid. The higher temperature, the higher concentration, the lower recirculation time you can use. But it also depends on how thick layer you have of your rouging. So I can't say exactly what is needed, because you have to try and test to figure out, because it depends on a lot of different variables. And I hope that answers the question.
So Aham asks a related question: what is better, commercial acids or formulated acid detergents to remove de-rouging?
Yes, I mean, commercial acids, that's typically a blend, a phosphoric blend, which is good. But if you use a standard acid, citric or phosphoric acid by itself, or if you blend it by yourself, maybe if you should go for a blend, it's better to use a formulated acid. But if you stick to phosphoric or citric acid with the concentration that is here, it really doesn't matter if it is a commercial or formulated acid to remove the rouging. That's what I have seen, because it's not really complicated. It's just an acid that can attach or dissolve the ferrite ions from the surface and in the rouge.
Thank you. And Saj Kumar asks, what is recommended rouge inspection frequency in WFI loop system?
That's also a very good question. And I would say there are no recommendation. It depends very much from system to system, how often or how frequent you should measure. If you see that you have a lot of problem with rouging, probably you should have a more frequent inspection. I would say most common is that you inspect the system when you do a maintenance, which, if it's not too long intervals between the maintenance, there are some companies that are extreme, that is actually doing maintenance every 3rd month, where they are replacing the diaphragm. Then this could be up to every 6 months or every year or yearly. And I would say most common is probably to do a maintenance yearly. And then you look for rouging in the system visually. Now it's becoming more and more of this rouge measurement system where you have the possibility to measure. But again, if you really would like to have exact measurement, you need an invasive system, or where you actually measure the surface, and then it typically needs to open up the system anyhow, and need to check. You can check it visually as well. So it's a very good question, but I'm afraid I cannot give you a very good answer. I still think it should be. Maybe what is also good to add here, in the system where you have rouging, water for injection system, where you're mixing it with your medicine and you have to secure that you don't get any particles in your medicine, you typically put the filter outside the system, and just outside the point of use. You put a filter to secure that no particles is coming to your medicine. That if you have rouge, you need to have this filter. No matter how frequent you do inspection, you need to have this filter to secure that particles is not coming into your medicine. And also when because you remove this filter, you replace it every time. And when you replace it, you also see if you have rouge particles in this filter. So I would say the best way of doing measuring is actually to check the filter that you are every time you replace it, and it's the cheapest way. You still need to have the filter anyhow, and then you have a very high frequency of the inspection. So that's probably should be my recommendation.
Thank you. And on WFI, Shirley Chow asks, the WFI system is operating 24/7. Rouge unavoidably forms. If we have to de-rouge and passivate every time we find rouge, basically we need to do that every year if we perform a visual inspection. This is very costly and time consuming. A shutdown is usually required to do this. So it asks, is there no recommendation for a more quantitative acceptance criteria?
Also very, very good question, and we have to think about what does the regulatory standpoint say here, and what they mainly say, you have to avoid particles in injectable or ophthalmic solutions, and the best way to secure that you avoid this is to have a filter. And as you say, with the water for injection operating 24/7, you will probably get rouging in your system. The most important is the particles. Secure that they don't come into the medicine, because that could harm the patient. So you need to use a filter. The other thing we need to think about is what the GMP say about equipment, that you can have a surface that is more difficult to clean if you have a lot of rouging, and that could increase the bacterial contamination in the system. So I would say, apart from having a filter securing that you are not having any particles in your medicine, the other thing is to secure that you don't have any problem with the bacteria. So if you don't have any problem with the bacteria, that the bacteria count is increasing to an alarm level, then you don't need to do a repass, de-rouging. So I think that should be the guidance when it is time for de-rouging. But of course, every time you do service and maintenance of the system, when you drain the system and when you replace shaft seals or diaphragms, you should take the opportunity to also do a de-rouging in the system. But apart from that, if you have the filter removing particles, if you don't have any problem with the bacteria content, then you don't need to do a de-rouging until you open up the system for service and maintenance. But there are no regulatory guidance. It's just to secure that you're following. It should be possible to clean. You should not have too much bacteria. So no strict guidance.
And the follow-up to that question is about, what about the use of online rouge monitoring instruments now available on the market? What do you think about their usage?
Well, I think they are good. Let me see, we have the measure rouge here. What could be interesting is the electrochemical impedance spectrometer, because it's a non-invasive. and it's measure the actual source for the rouging. It's measuring on its surface analysis and not a process fluid analysis, because the process fluid analysis they can be good, but they only give an indication. They don't give exact figures on how much rouge you have in the system, while the solid surface analysis, they give it. But on the other hand, as I mentioned, if you have a filter which you have in the point of use, if you're mixing with the injectables, then you will see it in the filter if you have rouge in the system. When you do maintenance, when you're placing the PTFE diaphragm in the system, you will also see if you have rouge on these diaphragm. So the question is, if you need it, it could be nice, but it's you can also do without them, because you have other ways of controlling, like in the filter and in the diaphragm. Not to oversell these. Probably the one that is selling these equipment, they say it's a must, but
okay.
Yeah, I should. Yeah, that's what I say.
I think that relates to Anil's question about early indicators when there's a rouge problem in the water system, and early signs showing in the water testing results. We've got a question, two questions relating to ozone. Thomas asks, how about rouging by storage under ozone? And Fernand too asks, if we use ozone for sanitation, whether it will ozone accelerate rouging?
Yes, there are tests, an indication, and also a natural explanation, because when you have ozone or O3, that will speed up the rouge formation as well. So it does. The more oxygen you have in the system, the bigger risk you have of getting this ferrite oxide or ferrite 3 oxide. But on the same time, we can say the more ozone you have in the system, the more easier it should be to create the passivating layer. But it's a mix there. What does it generate first? And it has been seen that ozone will increase slightly, not a huge amount, but slightly, similar to temperature. It will increase the rouge formation, like in the same way as the temperature are doing.
Thank you. Shri asks about the pumps of WFI is sometimes the first point to get rouge. OSOT, correct? How often to inspect this pump? Any recommendations?
Yeah, it's very interesting to mention the pumps here, because that's where you often see the rouge. The problem is seldom in the pump, but you can imagine when the water comes here and suddenly poof or smashed into the impeller in the pump, and then it's thrown, circulated in the pump, you're smashing all these rouge particles onto all surfaces in the pump. And it's typically, I had a picture here somewhere about the pump and rouge in the pump. It should, yeah, it's this one. You see it everywhere in the pump. So that's the first thing. If you see this red color in the pump, it's probably not developed in the pump. It's just that it has been deposited in the pump. And the question was also, is it a good indicator? Or sorry, Linda, you have to remind me what was it more than, was it for indication? Was it a good indicator, or what was the?
Sometimes the first point to get rouge.
Yeah.
How often to inspect this pump? Any recommendations?
Yes, this is typically the first where you can see it, and how to inspect. Well, it's when you do maintenance, the same thing as you can also check on the PTFE, and then of course you should check the pump, because normally when you do maintenance, you should take the opportunity to change the shaft seal in the pump, because that's wears down quite fast, depending on the temperature in the system. But these pumps are operated 24/7 and typically at high temperature, and then you have a quite high wear on the shaft seal. So you should open up the pump when you do maintenance. You don't need, as I mentioned in all the other questions, that you don't need to have a special check or control of Rouge in the system, visual and invasive control. You only do it when you do service and maintenance. And then you must separate the pump or disassemble the pump to check for the rouging and also replace the shaft seal. So do that in the same time. That's what I would recommend.
Thank you, Per-Ake. We are out of time, actually. It's 5:30 now. There are still quite a few questions in the chat, and if anyone would like to still post more questions, Per-Ake and the team from KHI will be able to come back to you with a fuller answer and to follow up with you. And in the meantime, he also wants to ask you some more questions. Just 2 questions, if you'll please stay with us for another minute or so, because this will help in the future.
Yes, and this question is, would you be interested in another webinar like this together with ISPE and Alfa Laval? Please let me know if that could be of interest, yes or no, or maybe. And if so, the second question here, if you can multiple choices here, check topics that might be of interest for you. So check mark if it's microbial control in water system. I went slightly into that, talked about bacteria, or it could be more deeper into stainless steel and welding in pharmaceutical system, which could help more deeper into avoiding rouging or avoiding other problems. So let's see what we get here, and it was very happy to see that you would like to listen to more webinars with ISPE and Alfa Laval, and quite high on microbial control, but also rather high on stainless steel and welding and hygienic system design, and also mixing and agitation in biopharmaceuticals. So very good, I'm happy to see this. Thank you very much. You also have contact details here to me with my phone number and email address, but also to our Alfa Laval salespeople in Singapore and in Indonesia. So Mas in Singapore and Agus in Indonesia. And you can also contact our authorized distributor and service partner, KHI and CHQ, and you have the contact details here.
Thank you for that, Per-Ake, and thank you for a very comprehensive and very clear presentation. I hope that everyone has enjoyed the session today. We thank you for your questions and for taking part, and we look forward to further opportunities to share your experience with us. Without further ado, we will be ending the session, but don't fear, we will be sending you a follow-up email with a link to the recording as well as to the presentation materials and the contact details for the team so that you can follow up. Please do help us to fill in the survey results, survey form that we will send you, as well as it's on the chat here if you want to just click on it and complete that. That will help us in future sessions. So thank you all for your time. It's pushing on for evening for us in Asia, and for Per-Ake it's kind of the beginning of your day. So we wish you a good rest of day, and to all of you wherever you're joining us from, thank you for your time, and we hope to see you all again.
Thank you very much.